All right, so today we're ready for chapter 2 at long last. We had a very long overview of functions of different types, which you'll need throughout the rest of this course in Calc 2 if you go that far. So here we're going to introduce a very important concept in calculus, which is called limits. So a lot of the concepts that we'll be seeing in calculus are actually based on the concept of the limit. And so basically, the idea here with the limit is that you have to imagine that you've got some kind of a function. Let me see if we can draw a quick sketch here. Let's just say, to keep it simple, it's y equals x squared. So imagine you wanted to know, here's x, and let's say this is 2. And of course, this would be 4, because if f of x is x squared, then f of 2 would be 2 squared, which is 4. So a limit is asking the following question. Let's say x is increasing, or actually, suppose x is over here on the left somewhere, and it's slowly heading towards 2. So let's say initially x is down here somewhere at -1, and it's slowly creeping up towards 2. The question is then, what is happening to y as we get closer to x equals 2? What function or what value are we approaching on this curve or parabola in this case? So we would say that the limit of this function as x approaches 2, or the limit of x squared as x approaches 2, is equal to 2 squared, which is 4. Now, the interesting thing about this is that this is true whether x is increasing or decreasing. Yes, in other words, if x was initially, let's say, 4, it's still, as x gets closer and closer to 2, any way you look at it, y is getting closer and closer to 4. So the limit, as we get closer and closer, you have to imagine we're getting infinitesimally close to 2 from either direction. And while that's happening, y is getting infinitesimally close to 4. And so that's what the concept of the limit really is in a nutshell. As x converges to one value, what is happening to y? Okay, now this is a very simple case, of course. We have much more complicated cases to consider. But you'll notice that a lot of the results as we go along, especially in the next chapter, ultimately depend on this concept of the limit, because the definitions that we'll be looking at depend on what's happening to y as x gets particularly close to a specific value. Now, in order to introduce this topic, we're going to start by reminding ourselves what a secant line is. Okay, and then, because we remember what a tangent line is, let me just quickly review that for a second. A tangent line is very straightforward. Imagine again, we have the function y equals x squared. Now, without the axes here, let's say I want to know, actually I could keep the axes in here. Let's say that x is 1 here, which means that actually y is equal to 1. A tangent line is simply a line that just touches the curve at that point and nowhere else, right? So it's not perfect, but that's not too bad. So this is a tangent line because it touches the curve at exactly one point. Now, and we'll see why this is so important, by the way. This is going to take on a huge role in chapter 3, this concept of the tangent line. A secant line is a little different because with the secant line, instead of touching the curve at one point, it actually cuts through the function twice. Okay, so that means this is a secant line. All right, so in the next slide, we have a graph of the secant line for some arbitrary function f of x. So you can see that the blue line is the function f of x. And then we have the points x f of x, a f of a is just some constant. And so the slope of the secant line between those 2 points, because it's a straight line, it's just y, delta y over delta x. And that means that we have f of x minus f of a all over x minus a. Okay. Now, imagine that we were to draw, sorry, another secant line up through here, let's say. And the 2 points are, let's say, here and here. Now, if you notice what's just happened is that the a and the x for this new case, I'll tell you what, let's call this a1 and x1. This will be a2 and x2. The slope of the second line I've just drawn is going to be f of x2 minus f of xa, f of a2 rather, all divided by x2 minus a2. Now, the important detail here is that x2 and a2 are closer to each other than the original x and a. And so as a consequence, the secant line is closer to the curve. So in other words, this red line is not really that close to the curve. The second secant line is a little bit closer because a and 2 are closer to each other. So what's going to happen here is that if the distance between these two continues to shrink, the tangent line will eventually become the secant line will eventually become a tangent. It will exactly touch the curve at that one point. So you can easily imagine, I mean, it's very hard to draw it right here, but if I keep letting the points get closer and closer to each other, the resulting secant line will eventually be right here. There'll be a single point where it actually is touching the curve, and that it becomes a tangent line. So as we let the distance between the 2 points get closer and closer to each other, the secant line is getting closer and closer to a tangent line. Actually, yes, here they've done something like that. And eventually, yeah, the last one is actually a tangent line. So that tangent line plays a very significant role in calculus. That's what we're actually interested in. It's the slope of that tangent line that we really care about. That's what we're after. That slope will prove to be hugely important. In fact, just as a sort of a forecast of what's coming in chapter 3, the slope of this tangent line is known as the derivative of x, y with respect to x. Now we'll have a very intense conversation about this in chapter 3, but the word derivative here is what we're after. Derivative, essentially, think of it as representing the instantaneous rate of change of y due to an instantaneous change in x. We're trying to capture how sensitive y is to changes in x. Okay, and we'll see that we will derive this whole concept with limits, but ultimately we'll end up using algebraic formulas to calculate derivatives. So every function, as long as it's continuous, will have derivatives at every point, and those derivatives will prove to have extremely useful information for us. Just as a simple example, let's say from economics, if I wanted to know how much it would add to my costs if I try to produce one more unit of my product, what I'm essentially doing there is calculating a derivative. Now, there's a change in my total cost due to a change in my total output. We can calculate that with a derivative. Okay, so this is going to be hugely important as we go along. But before we do that, we're going to introduce the concept of limits. The limit is the value of f of x as x approaches a specific value. So that, as we've said, now let's take a look at this case. We got a function which clearly has a discontinuity in it. This function is defined everywhere except x cannot be equal to 2. Now, what's interesting is that if you take this function, you'll notice that if you divide x, or if you take x squared minus 4, it can be rewritten as x plus 2 times x minus 2. Now, you can prove this with FOIL, but what you've done here is you used a process called factoring. And so let me just double check real fast that we haven't goofed it up. We'll use FOIL to prove that this expression does in fact equal this one. So the first would be these two. Outer is these two. The product, that is. Inner would be these two. Positive 2x. And then last is these two. And of course, last means the last term in each parenthesis. So when you add these up, you'll get x squared. These cancel out, minus 4. So what that means is that we do indeed have x plus 2 times x minus 2. So this function x squared minus 4 over x minus 2 is the same thing as so it can be reduced to x plus 2. So now x plus 2 is a continuous function, but remember the way this function was originally defined, we have this problem of x minus 2. So what you're going to wind up with is y equals x plus 2 defined everywhere except there'll be a hole right here where the function is undefined. Okay. So right here, we'll have a single hole in this line. And this is what it looks like. Now, we already know how to figure out the domain and the range. The domain is all the values of x. So the domain is all values of x except 2. And then the range would be all values of y except for 4. Okay, so that's written in the following way. Okay, all real numbers except 2. And down here would be all real numbers except x equals 4. Now, here's where the limits come into play. Again, you have to visualize that here's x equals 2. Here's x equals 4. Suppose that x is approaching, it's whatever it is right now, it's increasing and getting really close to x equals 2. At the same time, though, that means y is getting really close to 4. And we're coming from the other direction as x is shrinking to x equals 2. Y is also shrinking to x equals 4. Now, the limit then of this function as x approaches 2 is going to be 4. And what that means then is that as x gets infinitesimally close to 2 but doesn't quite reach it, y does the same thing with 4. Okay, so in other words, so we're getting really close. The distance between x and this 2 is infinitesimally small. The same thing is said to be true of 4. Oh, hold on. I just realized this should have said y equals 4. So therefore, the limit is equal to 4. And think of it as not what is y equal to when x equals 2? What is y approaching when x is approaching 2? So the key there is that you never quite reach 2 here. You're getting infinitesimally close to x equals 2, which means that y is getting infinitely close to 4. And therefore, we say that the limit of this function when x approaches 2 is simply equal to 4. Okay, so even though there's a hole here, the limit is still 4. Okay, because we're never quite touching 2. We're getting close, but not quite reaching it. And therefore, y gets really close, but never quite reaches 4. Okay, now here's another interesting one. Absolute x minus 2 over x minus 2. Now, this is a very bizarre little function. Clearly, x cannot equal 2, so you can rule right out. The domain is negative infinity up to 2, 2 up to infinity. In other words, all real numbers except 2. Now, the range is very strange in this one. Let me show you the graph real fast. The range basically is restricted to the two values, 1 and negative 1. Okay, it's hard to tell just by looking at the function, but that's all you've got to choose from. It's like a graph. It has two sections to it. And what you'll notice too is that as long as x is strictly less than 2, y equals negative 1. When x is strictly greater than 2, y equals positive 1. So this is a piecewise function. Also, if you notice, it is discontinuous at x equals 2. Now, here's the bizarre part. The limit as x gets closer to 2 from the left is 1. The limit as x approaches 2 from the right, as it's called, is positive 1. Okay, so in other words, the limit of f of x as x approaches 2 from the left, I'll put that in parentheses, or quotes rather, to indicate that this is very informal language, although all mathematicians use it. From the left simply means that x is increasing. Okay, in other words, it's coming from the left of the real number line. And up here, and this equals -1, as you can see. It's getting really close, but never quite reaching -1. Whereas up here, the limit of f of x as x approaches 2 from the right, we call this, is +1, because we're getting really close, but not quite reaching 1. Now, by the way, I just want to introduce some notation here. Up here, we saw that the limit as x approaches 2 is 4. That's the notation. The limit as x approaches 2 of our function is 4. But when we are trying to indicate that we're coming from the left or the right, what we do is this. This is approaches from the right. And this is how you would write. Oops. The limit as x approaches 2 from the left. Now, in this case, if you notice, they were equal to each other. That's an important detail. They equal each other. Therefore, the limit, now if you notice here, it just says 2. That means coming from either direction. Is therefore equal to 4. Okay, now there's the limit coming from the left is 4, the limit coming from the right is 4. Therefore, the total limit, or the two-sided limit, we sometimes call it, is equal to 4. These could be considered one-sided limits. Now, here's the important detail. In order for the two-sided limit to exist, the limit from the left and the right must equal each other. Okay? If they are different, then the two-sided limit is undefined. Now, most of the time, I mean, we'll be interested in two-sided limits, but it's important to note that we can also calculate one-sided limits for very strange cases. The 1 and 2, there can be different limits coming from either direction. And when that happens, there is no single limit. There's no two-sided limit. There can be a left and a right, but there cannot be a two-sided limit in that case. They have to equal each other. So in other words, the whole point of this example is to show that that's exactly what happened here. The limit as x approaches the 2 from the left was -1. The limit as x approached 2 from the right is 1. So they're not equal to each other. Actually, let me clean this up a little bit. I want it to be as neat as possible. So the limit as x approaches 2 from the left is not equal to the limit as it approaches from the right, which implies that the two-sided limit does not exist or is undefined. Okay. Wow. Let's look at this next case. So by the way, you're going to see pretty soon that a lot of these limit cases are actually very straightforward. As long as you don't have these bizarre functions, most limits are actually very easy to calculate. But we do have to be aware right up front that we can run into problems with these bizarre discontinuous functions. So like here's another one. Now this is the function y equals 1 over x minus 2 squared. Now clearly, the function itself is undefined when x equals 2. The domain is everything up to but not including 2, and then from everything above 2 to infinity. So what if we wanted to take the limit as x approaches 2? Okay, now 2 is where the asymptote is. So this is an unusual case. The limit from the left, now this is 2, by the way, don't forget. Where is it going? As we get closer and closer to 2, the function is converging to infinity. And same thing from the right. The curve goes up and up and up forever. It's also infinity. So here, what we're going to say is that the two-sided limit does exist, but it's equal to infinity. Okay. So in other words, it does exist. It is defined, but it is equal to infinity. Oh my God. So yes, you do run into this too. All right. So anyway, so with all that background, we can start by looking at the formal definition of a limit, and then we can start to actually do some calculations. So we have, first of all, this is how it's written. Just in the most general possible case, the limit of f of x, whatever it is, as x approaches some constant a, is equal to some constant L. This could be any function, like we had before. You would have written the limit as x approaches 2 of f of x, which is x squared, equals 4. Now, as we've already discussed, we have two-sided, this is a two-sided limit, by the way. One-sided limits means we're approaching from one direction or the other, but not both. This one implies, as we've seen, that it's approaching from either direction and they're both the same. Okay, it's like whatever we found, the limit is the same coming from both directions. So think of this as a two-sided limit, although sometimes we simply call it a limit. Don't normally use that adjective two-sided unless there's some reason why you need to be crystal clear about it. Usually when you say limit, you mean two-sided limit. On the other hand, the one-sided limits, you always have to describe it as a one-sided limit to make it crystal clear what you're referring to. So whenever you hear the word limit, we're going to assume that it's two-sided unless it specifically says one-sided. So as we saw already, coming from the left or from the smaller values, is that little negative sign. That means X is coming from this direction. And in this case, it would just be 4. The limit would be 4. And that naturally enough means that the other one coming from the right oh, sorry, that's 2. That would be this case. Okay. And so again, the terminology is that when we're approaching from the left or the right, we call that a one-sided limit. Coming from both directions is a two-sided limit. And as we've already discussed, a two-sided limit or just limit only exists if the limit from the left equals the limit from the right. Okay. So that is absolutely required for the limit to exist. It must be the same coming from both directions. Now, we can have infinite limits, as we just saw, if the function is converging to infinity, meaning it's approaching an asymptote of some kind. And sometimes it can be approaching infinity from just the left or just the right, or in the case that we saw, it's coming from both directions. So we can always end up with infinite limits. That's always a possibility. And when that happens, well, you can see the notation would be here coming from the left, as we saw with our last example. Coming from the left, it goes to infinity. And coming from the right, if we had this, by the way, this is not the function we had earlier, but here the asymptote is 0. So that means that the limit of this function, 1 over x squared, would be infinity. And then similarly, if we had the function y equals 1 over x squared coming from this direction. Oh, wait, I'm sorry. It looks like I got it backwards here. This one is positive. Oh, no. I see what happened. Okay. Sorry, my confusion. We're still referring to the left here in this graph. From the right. Okay, now we're good. Okay. That's what we have here. Okay. All right. So then we bring them together and we end up with this result. Now, sometimes it's possible for the function to approach negative infinity too. So we had something like this. That would be negative 1 over x squared. Then you can see they'd both be negative infinity. Because they're both decreasing to negative infinity. Oh, actually, this graph belongs in the next slide. Let me move it down here. There we go. That's what it would take. Okay, that's better. So y equals all right. Now, here's some cases that will result in infinity. And this one we've seen before. Remember, we had 1 over x minus 2 squared. That's better. That's our asymptote. And so you can see in this case, we're going to have positive infinity from either direction. Now, if you notice here, as a rule of thumb, though, they're telling you now in our case up here, the exponent is 2. Now, if it had been, let's say, 3, then the entire graph would be reversed and you'd end up with something different. Okay, like, well, let's just try as an example. Let's go to Symbol Lab. And see what it would look like with an exponent of 3. So it's 1 over, okay. Here we go. Ooh, no, this is different, isn't it? What do you notice? Actually, let me grab this picture of it, I mean. So that vertical dashed line is the asymptote. So what you're seeing here is that now we can see clearly 2 is the asymptote in this function. The vertical asymptote, I should say. But if I try to approach 2 from the left, You notice the function is getting smaller. So what ends up happening is that this limit is negative infinity. But if I'm coming from the right, the function is getting larger. So therefore, the two-sided limit does not exist because they're not equal to each other. It's fine for a one-sided limit to equal infinity and even a two-sided, but this is different. It does not exist. Okay. So here we have another case. It's just similar to the one we just saw. Y equals 1 over x minus 5 to the 4th. So it should be pretty clear. This line, x equals 5, is the vertical asymptote. But it's also clear that the limit on this side, as x approaches 5, is positive infinity, because the function keeps getting larger and larger and larger without bound. And at the same time, though, when we come from the right, it's also infinity. So that implies that the two-sided limit does exist, and it's equal to infinity, positive infinity, that is. So the rule here is that when n is positive, not positive, even, then this function will converge to infinity, as we just saw. But when it's odd, it doesn't matter if it's 3 or 5 or 7 or 15, it doesn't matter what a is. We'll get the same exact situation, and these two will be different from each other, and therefore the two-sided limit does not exist. Okay. Now, here's one. I accidentally picked the same one. We just saw this one. You can clearly see that this is the function. All right, but let's just run through it one more time. Here's x equals 2 is our vertical asymptote. The limit as x approaches 2 from the right is infinity, and the limit down here and therefore the limit, two-sided limit, does not exist. All right. So now what we're going to do is see some actual formulas for calculating limits. In other words, this is all the theoretical background. And it's important. We have to understand what these limits are. But now what we're going to do is focus our attention on actually calculating them. And we're going to see that there's some algebraic rules, and they're very, very straightforward. I don't believe there's anything in here that's the least bit surprising. For example, the limit of a constant is just equal to the constant. Well, that makes perfect sense. The limit of 3 is just 3. All right, that's the end of the story. Okay, just 3. Now, what about more complex cases? Oh, well, how about a to the n power, x to the n power, rather? Well, what you're basically doing is you're simply evaluating the function at a. Okay, so in other words, the limit. Let's do a quick example here. As x approaches 5 of x squared would just be 5 squared, which is 25. Now, by the way, if you look at this function, you can see very clearly we're not going to run into any problems with asymptotes, which means the left and the right hand limits will equal each other. Okay, so the issues when we have the left hand limit and the right hand limit do not match each other will require there to be something strange going on with the graph, like an asymptote. For a polynomial like this one, that will never happen. Algebraically, you can factor out a k from here. In other words, this is, let's say, the limit as x goes to 2 of 3x squared. If you find it easier, you can simply rewrite this. You can evaluate x squared, the limit of x squared, and then multiply the result by 3. Okay. So, often, if you're looking for specific rules, the constant can make it harder to see what you're supposed to do. So it's often easiest to simply move it outside. So you can focus on the actual limit itself and then multiply the result by the k. And then if you have something like this, now again, really all you're doing is you're substituting a into this. So let's say I had, for example, the limit of what, oh, let's do this one. If you notice, this piece by itself, literally all I did was replace the x with a 2. And then I ended up with 4 in parentheses. I multiply it by 3, and I end up with 12. So it's very straightforward for this case. Again, I mean, 3x squared is a very simple polynomial. Polynomials are a breeze to work with. And here's another quick example. So here, for example, you would simply replace the x with a 2, and you'd end up with 32. And that's all there is to it. So for these simple cases, all you're doing is literally substituting the constant in to your x, wherever the x's are, and you'll end up with the correct result. Now, there are some rules that we need to know. Sometimes we may have a combination of limits. For example, we might find ourselves needing to combine by adding or subtracting limits, and it's a very straightforward process. So the limit of a sum can be written as the sum of two limits. Same holds for the difference. You can tell that's why this is here, by the way. This is the so-called plus and minus sign. It's just a compact way of saying that the limit of f of x plus g of x equals the sum of the limits. The limit of f of x minus g of x is the difference of the limits. Although if you notice, they both will end up having, they're both converging to the same value. Okay, we have to keep an eye on that. So let's try one. A very straightforward one. This is a polynomial. Now I can't combine these two terms, obviously, but what I'm ultimately doing is taking the limit of 3x to the fifth plus limit 2x to the fourth. Now, if you want to, not absolutely necessary. Sometimes with very messy expressions, this actually might be helpful to move the 3 outside. And so you've got 3 times 3 to the fifth, which is 3 times 243, which is 729. And then for this one, and again, this is not absolutely necessary. and then they add up to 891. All right, so far it's looking pretty good. But now, if this rule works for sums and differences, does it work for products? Well, the answer is yes. Okay. So in other words, the limit of a product is the product of the limits. Again, just exactly what you'd expect. All right. So in other words, you can break this up into two separate limits and multiply them out if there's some reason for it. But again, make sure that they all are converging to the same constant. So here's a quick one. So here we can split this one up into the limit as x approaches 2 of 4x squared times the limit as x approaches 2 of 5x cubed. So again, because these are polynomials, all you're doing is replacing this with a 2 and this one with a 2. So you've got 4 times 2 squared times 5 times 2 cubed. Okay, so this is 4 times 4, 5 times 8, 16 times 40, 640. Man, the rest of the course is like this. It'll be a breeze, right? No, but of course, sooner or later we'll run into far more complicated cases. But this is a good starting point just to get ourselves used to the concept of limits. And like I said, we're going to use them to prove some very important results. Math is a very rigorous discipline, as you know. And as you get deeper and deeper into it, you'll discover that pretty much we spend a lot of time not just using our results, but trying to prove that they're correct. And there's a very formal way of doing that. It's a very it's something that the advantage of this is that every single person can agree that this technique is correct because we can prove it. Literally, we can prove it. It's not like some other disciplines where there might be opinions getting involved. Here it's very different. Everything can be proven. Now, the quotients, same thing is holding here again. The limit of a quotient is the quotient of the limits. Of course, with the understanding that the limit, that's the only thing we have to rule out, is not 0, because some limits are equal to 0. So we have to just make sure that we don't end up with 0 here. Other than that, anything goes. Okay. So let's see, what is our example for this case? So you'll see we've got the ratio of two polynomials, and when we substitute 4 in here for x, we ultimately end up with, this is 7 times 16 divided by 3 times 64, 112 over 192, which is approximately equal to 0.583. All right, now I've saved the most interesting one for last. Luckily, it turns out to be very, very straightforward. Okay, although maybe it's a little different than what you're expecting. But again, it's a very straightforward extension of this stuff. Here's what's going to happen if we have an exponent. What if I have the limit of f of x raised to some power? Well, what that means is if I choose to do so, I can replace that with the entire limit raised to the nth power. Okay, so in other words, the limit of x, let's say raised approaching 2, of 3x squared, which is the same thing as the limit of x as x approaches 2 of 9x squared. If I prefer, I can rewrite that as the limit as x approaches 2 of 3x and evaluate that first and then square the final result. And either way, I'll get the same thing. Now, here, just be aware this only works for strictly positive ends. And you might say, well, what's the big deal? What's the difference? Well, there might be cases where one of them is easier than the other. Okay. So, in other words, it may be convenient um, to do one versus the other. Like, here's an example. We have this one. Now, here's what we're going to do. Let's do it individually. Let's do it two different ways. First, let's just leave it like this. And then let's use this approach. So here, what's happened is that you're going to have the limit. Actually, we don't even need to write this again. You would have 5, 1. Now you notice it's exactly the same thing. But again, algebraically, there may be times where one is more convenient than the other. So it's important to understand that the two mean the exact same thing. Okay. Now, this is that, by the way, that was 2A. Let's see what's coming up in 2B. Let me just open it up for a second. Just out of curiosity, because we're basically ready to stop right about now, but I just want you to see what's coming up in our next session. Where are we going with this? Oh, we're just going to do some more complicated cases. Okay. Um, oh boy, you can see it's going to get messy. That's all right. We're building up to it in stages so that we can learn it properly. And so that when we do run into these more complicated cases, we can figure out what to do about them. Okay. So yeah, I mean, it's just slightly more advanced cases. So we'll save that for next time. Okay. So anyway, in the meantime, we'll cut it off right here and I'll see you next time.